This lab's actually two labs combined. One is on thermal expansion and one's on Boyle's law. You'll start with the thermal expansion one. While it's heating up, I'll show you what I mean in a minute, you'll do the Boyle's law lab, and then you'll go back to thermal expansion. So your objective here is to calculate the thermal expansion of a metal rod. So the goal of this lab is to find alpha, the coefficient of thermal expansion. To do this, you're going to measure the original length of a rod, you're going to heat it up to find the change in temperature. Starts at room temperature, so T initial equals room temp. And then you're going to heat it up, and then you'll measure this change in length and solve for alpha, which you will compare to a known value from your book or the web or something like that. So your apparatus consists of this big long tube with this little speaker. We'll get into what that's important. This is an old headphone. It's probably older than, well, it's definitely older than you. It's probably older than your lab partner and you combined. So what we have here, there's a metal rod in here. First thing you do, disassemble the metal rod and measure L. All right, your initial L. First thing you do, take it out of this metal thing. All right, take it out of this. They're corks, they just pop off. This right here is a thermocouple. All that does is it measures the temperature. And thermocouple. It's one word, but I ran out of room. So you're going to measure the temperature at room temperature. This little piece right here is a caliper. I'll show you how to use that in a minute. It just measures the length of the expansion. And this is a water heater, so you'll heat up the water, starts at room temperature. Eventually this is going to be the temperature of boiling water. Couple notes on using this screw. There is a little piece right here. So what you're going to do, you will tighten it. This completes a circuit, and you'll hear a little click in your headset. So you tighten it, then you untighten it until you hear a click. Every time it connects or disconnects, you hear the click. And you tighten it again, and you hear it click. So tighten, untighten, tighten back. And then you'll use this micrometer. So the way this works, this is in millimeters. So what you're going to do, the first part right here, if we look right here, I'm going to call that, as long as you measure from the right or same side, so I'll measure from this outside, and I'm going to call that 5, 6, 7, I'm going to call this 7, right? So this is your first digit is 7, because it's a little closer to the 8, but it's not quite. So then you look at the end, and it goes all the way around, and let's measure from this side, right here. So that is 7, and from this side, we get our decimal points, just like a regular caliper, and I'm going to have 0.55 right here, and then we go 1, 2, 3, 4, 5, 0.55, 6, 7, 0.57, and an estimation number of 5. So my original length for L naught, for delta L only, I have 7.575 millimeters. Then what you're going to do, you are going to unscrew this, back it off, leave about 5 millimeters. Yeah, 5 millimeters, maybe 4 millimeters, 4 to 5 millimeters. That way when your rod expands, it doesn't squish it. And then you'll just repeat this process. Again, make sure you do this 3 times at least. The more is better, it'll lower your error bounds. So your thermocouple, you have backed off the screw. The thermocouple, by the way, the units are all wrong, so it doesn't matter which one you use. It'll start off flat line. I'll do this in blue. And then all of a sudden, you will see it spike. There you're going. So this just tells you when it's done cooking, when it's reached the temperature of boiling water. So this is the temp equals boiling. Now, a real important note, water doesn't boil at the same temperature. So this is not 100 degrees Celsius. All right? It's why there are high altitude directions on macaroni and cheese. It's based on pressure, and I am happy to talk to you about this later in class. So it's based on your atmospheric pressure, P0. So you'll measure it from a barometer. You measure this, and then look up your final temperature. All the thermocouple does tells you when it's reached the temperature of boiling water, but you have to figure out what that boiling temperature of water is. So notes on the procedure. Measure the initial length of the rod first. Do not measure the rod when it is hot, because it's hot. Self-explanatory. When you are tightening it, tighten to a click, loosen to a click, then tighten again. All right, just kind of go back and forth until you're pretty sure you've got it. When you heat it, back the screw off 1 to 2, sorry, not 1 to 2, that's about your expansion, about 4 to 5 millimeters. So 4 to 5 millimeters. And then get the boiling point of water from the barometric pressure. You have to look this up. We've got a very nice barometer. It's hidden in Westerman Hall, so it's a field trip. Hooray for that. Yay! So data collection. Your checklist. Barometric pressure from the hidden barometer. Check. Original length of the rod before you heat it up. Change in length. So this is using the caliper. And this uses a meter stick. And then you need your initial and final temperature of the water, which you get from your barometric pressure in a nice table. For your error analysis, error propagation like always, and then compare alpha to alpha from the book, from the internet. Probably don't just go ask random strangers unless they're reputable sources and not prone to just making up numbers. So while you're waiting, it takes some time for this water to heat up. So we're going to calculate the atmospheric pressure using Boyle's law. So the theory is that pressure times some volume is a constant. Or if pressure goes up, the volume of the gas goes down. You apply more pressure on something, you squish it. That's pretty much Boyle's law. For setting up this lab, you are going to take this tube. And this tube is not empty. We have filled it with air for your convenience. The farther you jam this tube in the water, the higher this goes. The little water inside the tube. Because you have more pressure pushing down. Remember, more pressure down, more pressure increases as you go farther down in water, a fluid. It's equal to the weight of the fluid above you. So the farther this goes down, the higher the pressure goes. Now, you're just going to record this every 10 centimeters below the surface. So you'll record right here, and this is going to go between 10 and 80 centimeters. And then you'll record this number. So you can figure out how much air is inside this tube. And as it goes up, the water goes up, you can see that this air column in here decreases. Now, when you are doing this, one partner is going to hold the tube right against the side. Right? It needs to be completely straight. Do not hold it like this, because the water will do this crazy thing. This is a big no-no. Always make sure that it's straight. Your data collection. You need to record what's your initial volume of that small tube, the length of it entirely, the depth of the bottom, this goes in 10 centimeter increments, how far the water pops up, and then you need the barometric pressure, and we'll get to why in a moment. So when you analyze this, Boyle's law says that pressure and volume is a constant, right here. So if we move V over to this side, this would be the pressure from the fluid. However, that's not the only pressure. You also have your atmospheric pressure. So that's your atmospheric pressure that you read on the barometer, because not only is it underwater, it's also under the atmosphere. Right? So volume, we're going to approximate V equal to L. And the reason we can do this is if you have some cylinder, the width of the cylinder right here stays the same. The only thing you're changing is the height of the cylinder. So we're just going to approximate this V with L. And if you graph this, you'll get a line. And this offset right here. So if you graph y equals mx plus b, this offset right here, and it's actually going to be negative b, but that's okay. Same formula applies. Again, let's double check if you go y, no, look, pressure on the y, m is going to be this constant right here, x is 1 over L, put that right here, 1 over L, and then b is what you're looking for. That is your barometric pressure, because that's the offset. So what you're going to do, compare your thermal expansion coefficient with accepted values, and compare your barometric pressure with the barometric pressure from the graph. Double check your error bounds, make sure it makes sense. Hope this helps, and I will see you in lab.